59. I'll just start by asking, can you hear me? I know you guys here in the room can probably hear me, unless you're having hearing problems. I'm asking in the chat. Can you hear me in the chat? So I see a yeah and a Y, so that's great. Okay, good. Thank you guys. So now that I know that you can hear me, welcome. We're doing MATH7502 again, and this is our practical session. I don't know if it's week 7 or 8. Which one is it? Week 8?
Yeah.
That means we've got a holiday coming up soon. Yeah, a much needed break. That's good to know. Okay, so we're in week 8. And today we have a new assignment to talk about, which is nice. So let's, I'll just let you look at it together with me, and then I'll present a couple of points about the first 2 problems. All right, so look, we've got 2 pages, all right? So make sure you've got 2 pages. Now they're all full. So there's much to do in this, even though there are only 1, 2, 3, 4, 5 questions. Okay, so I will be going over just some key points about questions 1 and 2, and then Walla will come up and talk to you about question 3. And then if there's any time, I might have a little look at question 4. Otherwise, we'll save 4 and 5 for 4 and 5 to introduce after the break. Okay, so that's the agenda for today. So let's begin. Now, I had a little bit of a time issue this week. So I did some stuff, then I printed it out. Quite big, right? So my hope was that by printing an A3, the text would come out a little bit bigger and I would be able to talk about it more clearly. But actually what the printer seemed to do is printed out an A4 size on an A3 size paper. So that didn't quite work out as planned, but it looks legible enough. Now, I'm tempted to just display that rather than write. I'll see how I go, all right? So let's just read this first question together. So it starts by saying, consider data points in the plane. So we've got 2-dimensional points, and we have n of those. Assume that you're searching for parameters. I hear myself, Walla, is that you? That's all right, we'll just wait. It's a little disconcerting to hear an echo of yourself, so I'll just wait for Walla to just turn the volume down a little bit. Okay, anyway, thanks. Great. Okay, so what we're doing, we've got a function. You're searching for parameters of a function f of x such that the sum of the difference of the squares is minimized. Okay, and in our case, it's a simple linear function, so this is a very easy exercise. So this is called least squares. Now, least squares, it can be done with calculus, right? And I'll show you a couple of those tools for getting it, just to build the context for you of this problem. But there's also a way to do it with least squares. And since this data science course deals quite a lot with linear algebra, that's the preferred method, is to use a matrix approach to solve this least squares problem. But I'm going to show you both approaches, all right? But the first thing is, notice this pseudo inverse, okay? And it's given by A with a superscript of a dagger, and then it's an inverse of A transpose A times A transpose. Now, this is mainly an expression in which you assume that the matrix A is not square. Because what this pseudo inverse does, and you can tell from the name pseudo inverse, it's a generalization of the inverse, right? Because when A is a square matrix, the pseudo inverse is the inverse. So let's just do that. So assume first that A is square. Okay, and then let's just note what this is: A transpose A inverted, and then A transpose But if it's square, right, then we can take this inverse. So this here is a square matrix, and that inverse can be applied to both of those, right? Because the inverse of A exists in this case. So then this is equal to, remember we swapped, so it's A inverse, and then A transpose inverse times A transpose. And then these two cancel one another, right? In other words, you get the identity matrix from that because they're inverses of one another. And so what we have is a inverse, right? But so in other words, a dagger or pseudo inverse is the inverse when A is square, right? So it's a generalization of the inverse of a matrix. And now what it does when A is not square. Okay, hang on, I'll backtrack. So if you had something like AX is equal to B, right? And you wanted to solve for X, well, you would multiply by the inverse, right? So you'd have A inverse A, X is equal to A inverse B, and then you get X is equal to A inverse B, right? Great. And so this is when A is square, right? But this is also nice when A is not square because applying the pseudo inverse to this should give you a best fit solution, all right? So that's the connection here. It gives you a best fit solution when the matrix A is not square. Okay, so I hope that gives you a little bit of context to this problem. Okay, so next what I want to do is show you some calculations. And I think I'll just grab my A3 paper and just show it to you. And then I can write in the margins. All right, so I got basically the same problem here. And then in your question, you're asked in question A, when f of x is just plain linear, as in beta 0 plus beta 1 times x, it says there's simple formulas for fitting, essentially. Okay, so use the design matrix, and now I've got it right here because you're directed to a text. All right, but here I give you the design matrix. Now, I've got a horizontal dot, 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 but what I mean here is a vertical dot, 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 just so you know. Okay, so here, I didn't have a symbol for the dagger either, so I just called it B. So this is the pseudo inverse here. Okay, so use the design matrix and the pseudo inverse to derive these formulas. Right, so the formulas, you're directed in the question to a text, right? I had a little bit of a problem finding that because, now I think it's Yoni's book, right? So let me just see. Yeah, SWJ, Yoni's Statistics with Julia, Yoni's book with Hayden. But it's a draft copy, right? And apparently I downloaded it a few weeks ago, and maybe he's added more since then, and I couldn't find what he was referring to here. So sorry about that. So I just had to go with this, being in a bit of a hurry. Okay, so anyway, so derive some formulas, right? So what I'll do here is I'll just go through the calculus of this, and then we'll see how it relates to this pseudo inverse, right? But I may end up having too much information here, so I'll probably have to chop it off a little bit soon so that I don't solve this for you, right? Because I don't actually know what the formulas he's referring to there are. But you'll find out, right? You'll go and find the right section of the text and do that. Okay, anyway, so what we want to do, basically, this is an optimization problem, right? So where do I start? I define this Q of beta 0 and beta 1, right? And I'll scroll up here a little bit so it's clear enough. I'll hide some of this text just so we don't get overwhelmed with hieroglyphics like you kind of do if you go to Rome. Okay, so I've introduced just a Q, right? Q of beta 0 and beta 1. Now you want to find the unknowns, beta 0 and beta 1. Okay, so we put this into the formula, or in other words, I'm defining this as the sum of those squares. And then I just sub in f of x. put it in right there. So I'm just subbing it in there. Okay, next what I want to do is take the gradient vector, right? Because grad of Q basically tells you when you have the partial derivative 0 and 2 perpendicular directions, and you expect to find a local minima when grad of Q is 0. All right, so you take partial derivatives of each one. Now this is fairly simple because we've just got a sum of squares. Okay, so now the gradient vector is just this, right? So it looks like an upside down triangle. That's called nabla. Nabla Q, it's the partial derivative of Q. Now with respect to the first letter is beta 0, and then likewise with respect to beta 1. Let's see if I can zoom in here because it's very tiny. Okay, so I calculate those partial derivatives then. Now, the chain rule comes into play, right? Because I basically pull down the 2 that's there, according to what differentiation tells you to do, and then multiply that according to the chain rule by the derivative of what's inside that square. Okay, now that's simple because we've just got beta 0 standing alone there. So the derivative of the inside with respect to beta 0 is just 1. All right, and so now remember, you're treating the xi and the yi as just numbers. Okay, so it's a sum over those, and so basically we pull the 2 down and we've still got the sum, except now we just have the inside of that. And it's very similar for the derivative with respect to beta 1, right? So we end up with this. However, the difference here is since we're taking a derivative with respect to beta 1, the derivative of the inside part of the function is xi, right, with respect to beta 1. So that's why we have an extra xi there that we don't have in this one. Okay, so now what we want to do is solve for beta 0 and beta 1 such that this gradient vector is equal to 0. Okay, so we can maybe expand this now and simplify. So at this point, perhaps I need to scoot this over and show you because this is a little bit of a larger expression once I expand that. But what I'm basically doing is I'm taking this one here and I am basically moving the beta 0 outside to the front of the sum. I'm basically factorizing in both cases, factorizing beta 0 out, factorizing beta 1 out, because it's a sum of n things, right? And they each have a beta 0 in them. And so if I ask how many of those beta 0s are there are n of them, right? And so that's why I have a 2n beta 0 there, and so on. I factorize the beta 1 out of the sum, and then I have this. And likewise with the y, I have this. Okay, and I do the same thing for the second coordinate, and that's just right here. Okay, great. So now I've got to see, I've carefully put these sums in brackets. And now you can probably see why I don't want to write this by hand. There's much to write. But you'll have access to the video of this. Okay, so anyway, I put these in brackets. So I'm thinking of this as a number now. Okay, I'm thinking of that sum, this sum, this sum, this sum, this sum as numbers. And so yeah, now we want to look at when this vector is equal to the 0 vector. Okay, so we set this equal to the 0 vector, and we have an expression, this equals 0 and this equals 0, right? So in other words, simultaneous equations in 2 letters. Okay, so they look like this, right? So just taking each of those and setting those equal to 0. And now what you want to do is rearrange this, and so that you can write this in a matrix vector form in terms of beta 0 and beta 1. All right, and you can probably see how to do that, right? So what you do is you take this one over to the right-hand side, this one over to the right-hand side. Those are numbers, right? And then you have something times beta 0, something times beta 1, something times beta 0, something times beta 1. And then you represent that as, and I'll just do some writing here. I don't want to show you more because I'll probably end up solving too much, if I think about it now, right? And I think this is a huge hint for you so far, right? Just to be able to understand what's going on. Okay, and now, so you end up with something that looks like this: beta 0, beta 1, and then equals something like this, okay? I'll move that into view. And yeah, and so your question next is, what is this matrix, right? What is this matrix? How does that relate to the pseudo inverse? Okay, so your next step, and I think at this point I'm going to do some handwriting here and not show you any more of my typing for fear of accidentally solving something. All right, but what I want to show you now is the next thing that you should look at is A transpose A. Okay, so what is that equal to? All right, so if we transpose that A here that we're given, then that transpose looks like 1, 1, and then dot, 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 and then 1. Okay, and I need to zoom out. All right, and then underneath that we have x1, x2, and then dot, 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 xn, and then we have A here, right? Dot, 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 1, and then x1, x2, and then dot, 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 xn. All right, and I should probably shift over the chat. Okay, and so you calculate that, and then you want to relate this back to this one in some way. Okay, so in other words, are those the same, and what can you do with that next, right? How do you relate that pseudo inverse? This is not the pseudo inverse quite, right? But it's related to this. This is part of that, part of the expression. Okay, so relate the two of those. So that's your next step. Okay, so I think that's all I want to say about question 1A, and I've already spent a lot of time, but at least it gives you a little bit of an intro to the question. All right, so let's have a look at B now. All right, so the next one says, under what conditions on x1 through xn does the inverse, okay, so this is the actual inverse of this product, does the inverse A transpose A inverted above exist? All right, so basically what you're looking for here is, well, you know that the inverse of a matrix exists if and only if the determinant is non-zero. Okay? So, but you don't want to separate those because the assumption here is that A is not a square matrix, right? Okay, so you work with that. When is the det of this not equal to 0? Okay, and then you want to think of this in terms of vectors and find a nice way to describe that condition. So that's all I'll say about that question 1B for now, right? Because you need to get your hands dirty and think about these problems yourself. But hopefully I sort of prime the pump here of your thoughts. Okay, so next question, see now formula 8.35 in chapter 8 of SWJ. Okay, so again, I couldn't find that one because I probably have a version that's a little bit too early, but I hope that you have access to that formula. Now, what do I want to say about that? Let me just find my notes. Okay, so I think I'm going to show you a little bit here. So basically, let's have a little read here. It presents an expression for H subscript II, the diagonal elements of the projection matrix. So this has an A in front of the pseudo inverse. Derive this formula. So I couldn't find the formula, but I could do some calculations, right? Which probably ended in the formula. Okay, so I'll just go over a few of those calculations here. Now we're question 1C. Okay. All right, so let me have a look at what I want to show you. All right, so derive an expression for the diagonal elements of that. Okay, so what I've got here, got part of this, right? So this is something we had before, right? And so I said, let this be PQRS. And then what I want to know, basically here I've got A, and then I've got A transpose on the end. And then I can calculate this out, right? So I can do the product of these two, and then I get this. And then I multiply this by this, and I get a very large expression. Okay, so the point here is maybe you can make this job easier for you, right? By introducing some letters like P, Q, R, S. And then you can get an actual expression for H, and then you're looking down the diagonal, and you'll notice a nice little pattern, right? So that's where I would go with this, right? But keep in mind, I haven't seen the formula given to you for H double I. All right, so I think I'll stop with that and have a look at the time. So I'm already 20 minutes in. Okay, yeah, look, guys, you'll have this on video tomorrow morning, I guess. Okay, so anyway, now let's have a look at the next one. I've got to leave enough time for Walla. All right, so this one here is about Julia. I'm not going to say anything about that one, I think, for now. So you've just got to do some Julia calculating that you find in SWJ, modifying the code. So that I think you should be able to do, and that's a good exercise for you. You'll be able to get your hands dirty with that problem and get better with Julia. Okay, so let's have a look at E. Assume now you wish to fit a quadratic to some data. Okay, so here the design matrix is n by 3. So I think now I'm going to show you what sort of the design matrix you'll be looking for. But let's finish reading. Repeat the fitting using this type of model. Display your fit model graphically. Okay, so you're sort of repeating what things that you did here in question 1D, but now it's got 3 letters. Okay. All right, but your hang on. This is what I want to show you from this point on. Okay, so here your design matrix will look like this. You've got something like what you had before, and then you're appending on this column that's got the squares of these in it. Okay, and so you want to express this in a way like you did for beta 0, beta 1, and then look at the code of the previous section. Okay, and then Yoni's got some remarks. See the end of the lecture that's after the quiz 2 for plotting with Julia. Okay, so he should have full details of how to do that sort of thing, because that question, I believe, asked you to plot something. Okay, now the question 1F, assume now that f of x is equal to beta 1x. Derive a formula for beta 1 using just the column vector containing the x's. All right, so here's some calculus. This ends up being not what you want. So I'm just applying a similar approach, but this is not what you want. Instead, what you want to do is take the pseudo inverse and do your calculations with the pseudo inverse on this one. All right, the formulas will end up being very simple. So this one here is not a very hard question. Okay, and so that's question 1 discussed. Now I'm going to leave myself about 7 minutes to talk about question 2. All right, so let's have a look at question 2, and we'll start by reading it. Consider a polynomial of degree n with real valued coefficients. P of u is the sum of these all the way up to u to the power of n. Okay, so they've got presumably not necessarily coefficients equal to 1, but some other numbers, real numbers, but then the last one is saying it's 1, okay? All right, and then we see, let n by n, the n by n companion matrix associated with this polynomial is given by this, all right? So let's just note what we have here. So inside here, we've got an identity matrix, right? So you could view this as a block matrix. We've got zeros down here, and then we've got negative of those coefficients. All right, and then our question, the first question says, present the companion matrix for the polynomial P of U is equal to this product here. All right, so basically what you want to do here is expand this out, right? Then you get the coefficients, A0, A1, and so on, all right? And then you substitute those coefficients in here, and basically that you're done at that point. But I should tell you that I think there's a little bit of an error in the presentation of this question. And it's not a major error, it's just a sign problem, as in a negative sign needs to go in to make this, you know, totally consistent. So I'll just refer to some notes now that I did earlier. All right, and I'll try not to show you what I've got above that. So, great, okay, so I want to start here. Okay, so here I've just got this represented as a block matrix, okay, so I didn't want to write a lot of things. So something is slightly wrong with the question as it is. It's off by a sign somewhere, okay? So I think you can work that out. You're all very smart. But basically, so if you expand this out, so the constant term coefficient is twice 7 times 9. And you can see that straight away. So 7 times 9 is 63. Twice 63 is 126. So you get 126 there and some other things, right? I won't do it because you can even do this by hand, right? And I just don't want to give you the answer. It's too easy. All right, but also the product of these minus u's is minus u cubed, right? And you notice straight away that you've got a minus 1 as the leading coefficient there, but the problem is defined to be in terms of monic polynomials, okay? So that's why I say it's off by a sign. So you'll have to fix that. Okay, so instead, what I'm going to do is I'm just going to change this here to Q of U is minus this, right? And now what we have is minus 126 plus ... and you can work out what's inside. And now we have plus U cubed. Okay, so now it's consistent with the definition. And so all you're doing is you're expanding this, working out what those coefficients are. And now you're just subbing those in, and it's going to look like this, right? Okay, so you can do that quite easily. All right, so, but you'll get a chance to correct the question a little bit later down the track. So you may want to do some of those other questions and then come back and fix this appropriately after you've done that. Okay, so the next one says, compute the characteristic polynomial for CP. Now, I just assume that this is talking about in the context of eigenvalues, right? Because that's what you've been studying here. And I guess the term characteristic polynomial, it's probably only for matrices and eigenvalues and eigenvectors. So maybe there is no ambiguity there. Okay, so, and then that would be the determinant of the matrix. Now, usually you have a minus lambda times I there, right? But let's just replace the lambda with a u, because you want this to come out in terms of u's anyway. Okay, so the determinant that we get here gives you this one, right? And then so that's pu, right? But I think instead what you want here is a minus 1 to the power of n times the determinant to give you something consistent, okay? So you'll have to play around with this to make sure you get the question right, and then you can solve the question correctly. All right, so the next one says, prove generally. Okay, so my thoughts are that minus 1 to the power of n times this determinant gives you back the polynomial. That's what I'm trying to say here, right? Where that polynomial is monic. But you can check the details of that, right? So the last thing I want to do is talk to you about how you go about proving that generally, right? And so I'm not going to write this. I'll just type. It looks like I've got 1 minute to cover this, so I can give well enough time. Okay, so basically, so So minus 1 to the power of n, then we've got this determinant, right? It's going to look something like this once you subtract the lambda times I, and we're treating the lambda as the letter u. So we get minus u down the diagonal there, right? But how do you take this determinant theoretically? So what I want to suggest to you is that you turn it upside down. Okay, you see what I've done there? I've taken the bottom row, put it at the top, and basically reflected about the middle. Turn the jth row into the, I guess, is it the n minus jth row? You see what I've done? Turn the whole thing upside down. Okay, but when you do that, those determinants not quite equal. They're different by a factor of minus 1 to the power of n. So you come out with this determinant. Okay, and that would make it more easy to get the polynomial that you're expecting to get, because remember how you calculate determinants, right? What you do is you start with this, and you cover up the row and the column that it's in, and then it's multiplied by the determinant there. And then you subtract the same thing when you do that with the next one, and so on, right? But those subdeterminants in there, they're fairly simple to calculate. Theoretically, they'll probably have something like plus or minus ones in them times a power of u. I'm just guessing, right? Because we know what we're meant to get. Okay, so you got to go through that calculation, and just some side notes, because you can see that this is Mathematica that I've worked in here, because I find it a nice one-stop shop for thinking about mathematics. I can just do some symbolic calculations when I think about this. So I've just taken some determinants here, right? Just to check that that I'm getting what I meant to. So, and you can see the results here, right? So this is the first one there, and then I turn it upside down and I do that calculation, right? And now they're different by a sign of minus 1, but 3 is odd, so that's okay. And then likewise, I've done something similar for 4 by 4, right? And I see that I get the same thing, but 4 is even, so that's okay. And so you get the picture there, right? Okay, so that's all I want to say, and I've gone a little bit over time, so I'll quickly turn it over to Walla if you're ready, Walla. Okay, great.
Now we need to move to question 3. Yeah, in question 3 they ask, consider x1 of n as the population of owls in hundreds at time n, and x2n as the population of mice in tens of thousands at time n. Assume the following model. They give you 2 equations. The first one, x1 of n equal 2 over 5, x1 n minus 1, plus 3 over 5, x2 n minus 1. This is the first equation. And the second equation is x2 of n equal minus 3 over 10, x1 n minus 1 plus 13 over 10 x2 n minus 1. There is a relation between owls and mice, because owls eat mice. So they give you a couple of equations, one for x1 and one for x2. They ask you, at the beginning they said, assume that at n equals 0, here, if we substitute n equals 0, we will get that x1 equal 2 and x2 equal 3. What the meaning of x1 equal 2 and x2 equal 3? This is, we have here, this is referred to owls, number of owls, and x2 refer to number of mice. Because they said here owls in hundreds and mice in 10,000, so this is 200, this is 2 means 200 owls and 30,000 mice. So this is the question. This is a dynamical system, and we need to solve different questions related to this question. They ask you, in part A, represent this is as a linear dynamic system. They give you, we need to write this system as xn equal axn minus 1. Here, we have 2 equations. The first one x1n equal 2 over 5 n xn minus 1, here x1, plus 3 over 5 x2n minus 1. This is the first equation. And the second one, x2n equal minus 3 over 10 x1 n minus 1 plus 13 over 10 x2n minus 1. In part A, we need to write these couple of equations as x of n equal A, where is A is a matrix, multiply with xn minus 1. So we need to write it as, here we have x1 of n and x2 of n. This is equal. We need to find the coefficient of matrix A, multiply with xn minus 1. Here we have x1 n minus 1, and we have x2 n minus 1. Okay? Here this is matrix A is 2 by 2. And the coefficient of matrix A are 2 over 5, 3 over 5, minus 3 over 10, and 13 over 10. So we can put here 2 over 5, 3 over 5, minus 3 over 10, and 13 over 10. To be sure that we write this system correctly, you can expand again. You can multiply 2 over 5 by x1 plus 3 over 5 multiply with x2. This will give you the first equation. To find the second equation, x2n, this is equal minus 3 over 10 multiply with x1 n minus 1 plus 13 over 10 multiply with x2 n minus 1. Be sure that you can find or you can write this is as a system x of n equal A times xn minus 1. This is in part A, and it's easy and direct. Everyone can find it. Okay. Let's move to part B. In part B, they ask, determine the eigenvalues of A. Here we found matrix A. We need to find eigenvalues of this matrix. Try to calculate the values of eigenvectors here, the values of eigenvalues by your hand. How to find these? To find the value of eigenvalues, we need to find eigenvalues of A. To find it, we need to find the determinant of matrix A minus lambda I. This is equal 0. Which means we need to subtract from the diagonal the value of lambda, and after that we need to find the determinant, and this determinant equivalent to 0. So we need here from this matrix A, we need to subtract from the diagonal lambda, and this is equivalent to 0. We mean 2 over 5 minus lambda, 3 over 5, minus 3 over 10, 13 over 10 minus lambda, this is equal to 0. And after that, you need to solve this determinant and find the values of lambda. Okay? I think you will get two different eigenvectors, eigenvalues. Just you need to find the determinant and calculate the value of lambda. It's easy also. Okay. In part C, they ask, find corresponding eigenvectors. We need to find the eigenvectors V1 and V2. In general, V1 related to lambda 1, V2 related to lambda 2. So we need to find two different vectors, V1 and V2. To find these vectors, we need to find eigenvectors. Just you need to substitute in the equation A, the matrix A, minus lambda 1 times I. This is multiplied with a vector x equal to 0. If you substitute the value of lambda 1 from this equation, you will get the value of V1. And to find the value of V2, you need to substitute in the equation A minus lambda 2I multiplied with the vector x. This is equal to 0. If you try to find the value of V1 and the value of V2, just it will be satisfy this equation. So you need just to move to matrix A, subtract the value of lambda 1, which we found it in part B, and multiply with x. Suppose x is u and v. This is equivalent to 0, okay? The value of V1 and V2 are not unique, maybe any numbers. For example, if V1 is 1 and 1, V1 also may be 2 and 2. You can multiply V1 with any constant. So it's not unique. To be sure that you solve correctly, you can check your answer using Julia. You can use here the code Eigenvalues, and here you can use the code Eigenvectors to be sure that your solution is correct. But try to use it by your hand. Try to calculate it by your hand. Okay. In part D, they ask, represent x0, 2, and 3 transpose as we need to write this initial condition, x0, yeah, this is given by x1 equal 2 and x2 equal 3. This is the same number, we put it here in a vector. x0 equal 2 and 3 transpose. We need to write this vector or the initial condition as alpha 1 v1 plus alpha 2 v2. We found the value of v1 and the value of v2 from part C. Just you need to write this vector x0 as constant multiply with the first vector plus constant multiply with the second vector. For example, if we have the vector 2 and 3 here, bar G, if we have this vector 2 and 3, we need to write it as alpha 1 of 0, this is a constant, times the first vector, plus alpha 2, 0, times the second vector. For example, alpha 1, suppose it at 3 times v1 plus 2 times v2. When you multiply this one together and add it, the first column the first row should be 2, and the second answer should be 3. Okay, this is the meaning of we need to write x0 as a linear combination between these two vectors. To be clear for you, for example, we can write the vector 2 and 3 as 4 times 1 and 1 minus 1 times 2 and 1. To be sure, 4 times 1, 4, minus 2 is 2. 4 times 1, 4 minus 1 is 3. So this is the meaning of x0. We need to write it by alpha 1, 0 of v1 plus alpha 2, 0 of v2. Okay, you need to find v1, v2, and then you need to look for these constants. This is part D. It's clear for you? Okay. Let's move to part E. In part E, they ask, now use diagonalization to compute explicit expression for x1n and x2n for any time n based on the expansion of x0 in the bases v1, v2 as in D. We need to use this expansion, and we need to write a general formula to find the value of xn or x of n. How we can do that? They give you that here matrix A is diagonal. We need to use diagonalization. In general, here we have from part A that x of n equal ax times n minus 1. If we try to find the value of x1, the value of x1 equal a times x0. If we try to find the value of x2, the value of x2 equal a times x, here 2 minus 1 is 1. And the value of x1 now is known. It's equal a multiplied with x0. If you substitute, you will get a times x0. This is equal a to power 2 times x0. If we try to find the value of x3 when n equal 3, you will get that equal a times x2. This is equal a times a squared times x0. So this is equal a to power 3 times x0. If you run this algorithm until xn, the value of xn equal a to power n times x0. They give you that we need to use diagonalization. We know that a equal, in general, a, if we need to use diagonalization, a equal p times d times p inverse, where p represent the, it's a matrix for eigenvectors, d is a diagonal matrix which contains just lambdas, p inverse also, which contains, which is a matrix for eigenvectors, just we need to take an inverse. For example, here b, it consists of v1, v2 until vn. All of these are eigenvectors. Times d, which is a diagonal matrix, lambda 1, lambda 2 until lambda n, and the rest is 0. And multiply with b inverse, which is the same, the matrix D, just we need to take the inverse of this matrix. Here we have the first vectors, the second vectors, all of these also eigenvectors until Vn inverse. Okay, this is the matrix, this is the value of A. Now, what's the value of A to power n? Because we're looking for A to power n. You proved before in the lecture that A to power n equal B times D to power n times B inverse. So this is the value of A to power n. Now let's return back to value of xn. The value of xn equal A to power n times x0. Just substitute the value of an here. This is equal P times D to power n, P inverse times x0. Now we need to work with this one to get a general formula. Let's try to find the value of P inverse times x0. P inverse times x0, what this is equal. From part 3, I think, we can write that the value of x0 as alpha 1 of 0 times the first vector plus alpha 2 of 0 multiply with the second vector. In this case, because just we have lambda 1 and lambda 2, if we have an n in lambdas, we can write it as x of 0 equal alpha 1 of 0 times v1 until alpha n of 0 vn, because we have n vectors. Okay, if you try to find the value of b inverse times x0, this will give you the value of alpha 1 0, alpha 2 0 until alpha n 0. Just you need to multiply b inverse times x0, you will get that equal alpha 1 of 0, alpha 2 of 0 until alpha n of zeros. And all of these are constant. This is the first step. Now we need to multiply b inverse x0 by d to power n. And we said d is a diagonal matrix which consists just with lambdas or eigenvalues. If we need to find a value d to power n times b inverse x0, this is equal, just we need to multiply each one by the value of lambda. This is equal lambda 1 to power n, alpha 1 of 0, lambda 2 to power n, alpha 2 of 0 until lambda m to power n, alpha n of 0. Okay? Now just we need to multiply by the matrix P. The matrix P, which consists of eigenvectors, just we need to multiply by this matrix. So P times d to power n, P inverse x to power 0. This is which equivalent to xn. This is equivalent to xn. This is the value of xn. This is equal to lambda 1 n alpha 1 of 0 multiply with p and b just consists with the columns which are eigenvectors. So the first items here multiply with the first vector plus lambda 2n alpha 2 of 0 multiply with the second vector until we reach lambda m to power n alpha m of 0 times Vm. So we can write xn as summation lambda I to power n alpha I of 0 times Vi, where I go from 1 to m. This is the general formula for xn. And the general formula here is equal summation from I equal 1 to m for lambda I to power n alpha I of 0, which is a constant, times Vi, which are eigenvectors. Okay. This is in part D. This is in part E, okay? If you try to expand, because yeah, just we have two equations, just x1 and x2, you will get that x1 or xn here, because just we have m equal to, this is equal lambda 1 to power n times alpha I of 0 or alpha 1 of 0 times v1 plus lambda 2 to power n alpha 2 to power, alpha 2 of 0 times v2. This is the value of xn, okay? Let's try to expand a bit. Here, xn equal lambda 1 to power n alpha 1 of 0, which is a constant, v1 plus lambda 2 to power n alpha 2 of 0, v2. Suppose that v1 is a vector. I will put some symbols. Here, this is, for example, lambda 1 to power n alpha 1 of 0. Suppose that v1 is v and mu. You will find it this, okay? You need to find the value of v1 plus lambda 2 to power n alpha 2 of 0 times v2. Suppose that v2 is m and n, okay? So we can write the value of x1 of n, which equal alpha 1 to power n alpha 1 of 0 times v plus lambda 2 n alpha 2 of 0 times mu. This is the first equation. All of these are constant, okay? All of these are constant. Lambda here, lambda 1 and lambda 2 are eigenvalues, which you will find it in part A. Alpha 1 of 0 and alpha 2 of 0, we need to find it in part 3. V1 and V2, these are vectors which related to lambda 1 and lambda 2. These are eigenvectors. And x2 of n, this is equal lambda 1 n alpha 1 of 0. Yeah, let's move here to another, because here we put, okay, mu and mu. Let's call it here x, for example. Here, okay. The second equation, lambda 1 to power n alpha 1 0 times x plus lambda 2 to power n alpha 2 of 0 times n. This is the first equation, and this is the second equation. But you will find that with a constant, not with these symbols. Why we try to expand? Because we need it in part F. In part F, they ask determine limit of n goes to infinity of the vector xn. What is the meaning of this vector? Here we have two equations, x1 n and x2 of n. You need to take the limit for the first equation, you need to take the limit for the second equation, and both will terminate to 1 point. Okay, just you need to find the limit for x1 n. This will give you an answer, and you need to find the value of limit x2 of n. Because here we have n, we need to know what's happened when n goes to infinity. Because will be a constant, this is a constant, this is a constant. You need to show what's happened when n goes to infinity and what that meaning, what the meaning when n goes to infinity. Okay, it's clear for you? Okay. The last thing, in part G, plot the trajectories of xn both in manner similar to figure 10.1 in SWG in the x1, x2 plane, and as function of n. Both the plots of x1n and x2n on the same plot. You need to draw x1n, x2n in the same plot. This is the first thing. The second thing, present the two alternative plots on this dynamical system side by side. You need to draw one for x1 and one for x2. Okay, make sure that the plots are neatly labeled and formatted. You need to become neatly, you need to label everything. The plots should show convergence to the limiting point found in F. You will show that in the graph that these x1 and x2 terminated, or they are goes to the limit point, which you try to find it when F here, part F, when the limit or when the value of n goes to infinity. I will give you just a small hint in this question. You need to return back to Julia book and see figure 10.1. At the beginning, to draw, you need to use some packages. You need to use some packages. For example, you need to use plots package. You need to use plot package, okay? Because here we have xn and x1n and x2, these are next value, which depends on xn minus 1 and xn minus x1 n minus 1 and x2 n minus 1. So instead of say x1, x2, you can put x and y. For example, next xy, we can write it as, here you will put the first equation, and here you need to put the second equation. You need to use also the initial condition, which is the value of x0. The value of x0 is given by 2 and 3. And we need to know the numbers of points. Suppose that the number of points is 100. You need to put tn, the last one, for example, 100. And after that, you need to use for loop. For example, the trajectories, we need to draw the trajectories. This is equal. We start with something for I. And 1 to n, the last items here, we suppose it's 100. The first thing, we have the initial point. We will iterate with the initial point. Here, the first items in the trajectory, the first one, this is equal x0. You need to work again and to find what's happened from 2 to the end. This is the first point. We need to solve it from 2 to the end. For example, we can say that for 2 and 2 until end, okay? And the trajectory in this case, the trajectory t, this is equal. Next, we need to use next algorithm here. Next, for the trajectories, for t minus 1, and you need to continue. We need to put n for this for loop, and after that you need to use plot code. Okay, this is for the first one. For the second one, you need to plot two figures, one for x1 and one for x2, and to be sure that when you plot x1 and x2, both have the same limits, and the limit will go to 1 point. This is some explanation related to question 3. Is there any question related to this question? Okay. Have a good day. Yeah, it's related to your question, I think. Hi, Sam, can you, yeah, they ask why you put n equal to. Yeah.
Hi, Jonathan. I see you had a question there. So I'll see what that relates to. But you say here...
I was just back in the, we were doing the calculus for the summations. I wasn't sure what the summing from I to, from 1 to 2, why it was 2 we were summing to.
Okay, let me just go back and have a look. Was it on question 1A?
Yeah, yeah.
Okay. So, now, so you mean two things there?
Yeah, one, why is n 2?
Okay, so the n there that's at the top of the sum, and it's really tiny, so let's see if I can zoom in here. All right, so that n is not equal to 2, right? The n at the top of the sum. That's
Oh,
just,
okay, sorry. I thought we said it was at one point.
I might have misspoken.
Okay.
But we have two things here because there are only two letters that we're optimizing for, right? Beta 0 and beta 1. So that's why the number of components of the vector is equal to 2.
Oh yeah, so but the line below, if we pulled out a 2 beta naught and a 2 beta 1, and where did we get that to?
So here we're just differentiating, right? So we're taking the partial derivative with respect to beta 0, say, right?
Yeah.
And using the chain rule, that means pull the 2 down. And then so you have 2 times that product there, because it's the sum of all these things, right? So you apply it on each of the summons. And so we have twice this, and then the derivative of the inside is just 1 in each case. So we have twice this sum for that. But then I think you're asking about the second part underneath that, right?
Yeah, I must have misunderstood. I thought we said we pulled out 2 somewhere because of n equals 2. So I think,
okay, sorry,
I think I'm good.
Yeah, okay.
Okay, all right, I think I'm good. Cheers.
Anything else?
All good, thank you.
Okay, so you had a question for Walla, though, it looks like.
She said because it relates to x naught.
Okay, so you got that answered properly?
Yeah, I don't know why it would change.
Okay.
Yeah, but.
Well, Wallace says because we need to find the general solution.
Oh, okay.
All righty.
Okay.
So now it's time to start this again. Are you guys ready? All right. So here we go. See if I can put this into place. Okay, so who have we got here? We've got Jingyi Lee. Are any of those you?
I'm maybe.
Okay, right. But are you also logged in?
No.
No, okay.
No,
All right.
okay.
Okay, so Jingyi Lee and Zhang Hang Lin, can you both hear me okay?
I think Jay lost class.
Yes? But Jingyi Lee, were you in the last session? No? Okay, so you're here for now. And Zhang Hang, you were in the last session? Yes? Okay, so Jingyi Lee is arriving now, is that correct? But Zhang Hang Lin was from the last session. Okay, so that's fine. That tells me that we're definitely going to go through this again. Okay, so, but I'll specifically speak to you, Jingyi. Okay, so here you've got another assignment, recently released. It's got 5 questions. And they're fairly straightforward. So I'll go through the first 2 with you, and then we'll hear from Walla, who will talk about the 3rd question. And then the questions 4 and 5, I think we'll end up leaving for after the break to introduce those. But of course, you're welcome to work on that during the break if you have time then. All right, so I think I want to try to scoot the chat over a little if that works. Okay, great. Okay, so our first question says, consider data points in the plane x1, y1 up to xn, yn. Assume you're searching for parameters of a function f of x such that the sum of these squares is minimized. Okay, then you've got question A, which says when f of x is equal to beta 0 plus beta 1x, in other words, just linear, there are simple formulas for optimizing beta 0 and beta 1. And then Yoni here says, see, for example, in his book with Hayden, it's a draft version, okay? You can see some examples of those formulas. Now, I had a hard time finding that because I think I've got an earlier version and it's a draft version. So I guess that made it difficult for me to find those. So what I'm going to do instead is just do some calculus and talk about derivation of such formulas. Okay, and I really hope I'm not solving this, but I don't know if I am. So the first thing I should start with discussing, though, is the notion of a pseudo inverse. Looking for some paper here, blank paper. All right, so the notion of a pseudo inverse, it's a generalization of an inverse because when the matrix A is square, it's the actual inverse. Okay, so just say first, assume, now this is information just for your sake, assume A is square. Okay, then what we have here is A dagger equals A transpose A inverted times A transpose. And then because it's square, we can apply the inverse to each of the inside in the brackets here because those inverses, actually what I should say here, square and invertible, right? I forgot that in the last session. Invertible. Okay, so then we could apply the inverse to each one of these, but of course we have to reverse that when we do this. Transpose, and then since these two are inverses of one another, that's the identity matrix, and so we end up with A inverse. And so you can see that when A is a square matrix and it's invertible, the pseudo inverse is the same as the inverse. But what's good about the pseudo inverse is it kind of gives you something useful when A is not square. And what it does for you is it gives you a solution to a least squares problem, okay? All right, so moving on, I said earlier I wanted to do some calculus here to show you how one applies the least squares problem. But I think what I'm going to do is, like I did in the last session, I'll rely on what I got printed out from earlier. And here I'm going to fold over what I don't want to show you first before I put it on the document camera. And incidentally, Jing Yi, just interrupt vocally if you want to anytime. You're the only one in here other than Walla, who is working with me. So yeah, if you have any questions about anything, we're here for you, all right? Okay, so what I'm going to do here, I hope you see this all right, but we might need to zoom in. So I've just got it kind of rewritten there. So the matrix you need to look at, the design matrix, is this one, right? It's got a column of ones, and then it's got x1, x2, and then I mean to have the vertical ... there, but it's horizontal in the way it's done, and then xn, okay? So this here is the pseudo inverse. I didn't have a dagger symbol in my typing, so I just put a B. All right, and so what we're going to do here is do some calculus here to show you the set of equations that you need to solve, right? Okay, so I'm going to introduce Q of beta 0 and beta 1, and so that is just this expression up here, the very same one. All right, and so what I'm doing is I'm subbing in this linear function here for the f. So I'm putting in beta 0 plus beta 1x there, and so it's just right here. Now, since I'm not going to reuse this, I can just draw on that. I might even do it with a red. It's a little clearer to see. Okay, so what we want to do now is take the gradient vector. Okay, and so basically when you take the gradient vector of a, say, 2 or 3-dimensional or higher dimensional function, you're taking partial derivatives in with respect to each of the variables, and you want to identify when those partial derivatives are equal to 0. So the gradient vector is just a collection of coordinates having these partial derivatives in them. Okay, so grad of q is the partial derivative of q with respect to beta 0, and then the same thing with respect to beta 1. And now calculating those derivatives is fairly easy. What we're doing is we're differentiating this sum right here with respect first to beta 0, right? So you've got a sum of n of these, where you put I equals 1 and 2 and so on. And so you can differentiate each sum end and then consider what it is generally, all right? So differentiating the first one, where, say, we have I equals 1, for example, we pull down the 2, right? Because we're taking a derivative of a square, but then we have to, by the chain rule, multiply by the derivative of what's inside the function. And that happens to be 1 in the case of beta 0. Okay, and so what we have there is twice this, the thing inside the brackets, but of course we have this sum still, right? We have a sum of these. And so we end up with that first component, the partial derivative of q with respect to beta 0, being twice the sum of these. Okay, and now likewise taking derivative of q with respect to beta 1, it's similar, except now we have an x1 next to it, right? And the reason why is because if we're differentiating this partially with respect to beta 1, the coefficient of beta 1 there is x1, right? And so by taking the derivative using the chain rule, right, we pull the 2 down and then we take the derivative of the function that's inside. And so that derivative is x subscript I, all right, which you think of as a number. And so, yeah, all okay, all right, so that's why we get this. Okay, so the next step is, now that we have the gradient vector calculated, what we want to do is expand this in a way that emphasizes the beta 0 and the beta 1, okay? So in other words, we can, we can factorize beta 0 and beta 1 out of parts of the expression. Okay, so now if I just look at the first part, so we've got twice the sum of the beta 0, but there are no x and y next to that beta 0, so that's, that becomes just adding beta 0 to itself n times, right? And so that one is just 2 times n times beta 0. Okay, now looking at the next part of it, we've got the sum of beta 1 times xi. All right, now we can factorize that beta 1 out of the expression, and so we get 2 beta 1 times the sum of the xi there. All right, and similarly, doing the same with the yi, we've got minus twice the sum of the yi. Okay, now we do just the same thing with this part of the expression, the second component of the gradient vector. Okay, so we end up with twice beta 0 times the sum of the xi, twice beta 1 times the sum of the xi squared, because there's an xi there and an xi there. In other words, we expand that in. Okay, and then finally minus twice the sum of these products. Okay, so what we want to do now is consider when we have the gradient vector equal to 0, and then write 2 equations. And you can see them written down right here, right? So in other words, this one equals 0, and the second component equals 0. And then what you need to do is express this as a matrix equation in terms of beta 0 and beta 1. And so it's going to look like something like this. You're going to have a 2 by 2 matrix here, and then multiplied by beta 0, beta 1, and then you have a right-hand side, okay? So in other words, AX equals B, where the X is this one. And you've got to solve that, right? And so what you need to do next is, how do you associate this matrix with quantities here, right, that are in this pseudo inverse? Okay, so what I suggest you do next is start to calculate things that are in that pseudo inverse. For example, because I mean, this is your solution here, right? This one right here, where you've got to fill in the gaps there, the blanks there, okay? But that's fairly easy. So next, I mean, you need to relate this back to the pseudo inverse, right? How does the pseudo inverse relate to this equation? Okay, so the big hint here that I'm going to give you is that you need to calculate A transpose A, all right? And so I'll just write out the first part of that. So if we transpose A, what we have then is 1, 1, and then dot, 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 1. Okay, and then we have x1, x2, and then dot, 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 xn. And then over here we have A, 1, 1, dot, 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 1. x1, x2, dot, 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 xn, sorry. Okay, and now you multiply those out, right? So I'll just give you a hint. So this one multiplied by this column here is the sum of n ones, okay? And so that's going to give you just the number n. All right, and so you can then calculate this. You'll get a 2 by 2 matrix. Can you compare that to what you have here? Right, and then you're not done there. You've got to then show how the solution relates to this pseudo inverse. Okay, so that's all I'm going to say about that, because if I say much more, then I think I will have given it away if I haven't already. So if I have, I'm sorry. Okay, so let's move on, and we'll look at the next part of this question. Okay, and I'll get some new paper and cover this up. Okay, next, under what conditions on the x1, x2 up to xn does this inverse above exist? All right, so you know that a matrix has an inverse if and only if the determinant is non-zero. So I suggest you start considering when is the determinant of that matrix non-zero. Right? In other words, the determinant of the matrix A transpose times A. And then you want to find a nice condition on that, right? Think about the vector x1, x2 up to xn, right? Does this have any special relationship when with something else when this inverse exists? Okay, all right, let's have a look at question C. Now, see now formula 8.35 in chapter 8 of SWJ. It represents an expression for HII, the diagonal elements of the projection matrix here. Now, part of that's the pseudo inverse, and then we've got an A on the left-hand side. Okay, derive the formula for HII, I suppose it says. Now, again, I had a hard time finding this in SWJ, because it's, I think, now I could just be silly, but I think because it's a draft and I downloaded it 3 weeks ago, maybe some more work has been done on it, and now there's an 8.35 and maybe there wasn't before. I don't know. It's possibly equally probable that I'm just silly and I missed it. Okay, so I don't know what that formula is, but what I can do is give you a few hints on this, right? Okay, and so what I'll say here, I'm going to do some handwriting at this point. Right, what I'm going to say here is to let A transpose A inverse be equal to P, Q, R, and S, all right? And the reason for doing that is because you know what A is, you know what A transpose is. It gives you more of a simple way symbolically to deal with this at first, right? Okay, so then what you're doing is calculating that A transpose A inverted times A transpose then looks like A PQRS A transpose, right? And remember that A was the vector with ones down the first column, x1, x2 to xn. And then here we have PQRS. And then here the transpose of that is 1, 1, dot, 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 1. Then we have x1, x2, dot, 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 xn. Okay, and then I just focus on this part of it first, so you can easily multiply that out. And then once you have that, you can multiply this one by the result, and then you can have the expression for, I guess, the matrix H. And then you can look down the diagonal of that and notice a nice pattern, okay? And then from that point, since you should know what is in what PQRS are, you can replace those by the actual sums that they represent, and then get a more precise formula for that. So I suppose that's what you're meant to do here in this question. All right, let's have a look. So we're on this one. Derive this formula. So yeah, I guess doing this process, that would be deriving that formula. Okay. So now the next one, and I need to accelerate a little bit here. I think I've been talking a little bit too slowly. 6:21 p.m. and I want to finish up by 6:30 to give Walla a good chance to talk to you, Jingyi.
Sorry, Sam.
Hi.
In fact, I just want to hear the question 1 because I have already finished question 2, 3, and 4.
Okay, sure. You're
yeah, quick. Yeah, yes, because Monday we have the document, right?
Monday you have which?
I have the assignment 1, 2, assignment 2.
You have assignment 2 on Monday?
I don't remember the date, but I finished yesterday. So I just have question about question 1. So now okay. I understand.
Okay, sure. So what would you like to ask about question 1?
Now I understand you explain very clearly.
Okay, so I'll reiterate here. You're saying you don't need us to talk about question 2 or 3?
Yes.
Okay, that's all.
Is that
that's
okay?
All right. So, sure. Okay, then what about question 4?
I also did it yesterday.
Okay, great. So then we'll just talk about question 1, and then once we're done talking about question 1, I guess we'll finish up early at that point.
Yeah, thank you.
Because I mean, there'll be a recording of the rest of what we did for everyone later anyway. Okay, so that's fine. All right, then let's have a little look at this, the next one. So this is question 1D. It says, consider listing 8.8 in the same book, SWJ. Modify the code in this listing to find the estimates of beta 0 and beta 1. Okay, so I'm just going to guess. Now, I don't have the text in front of me, and I never ended up finding the right place in there anyway. So I can only guess what's in there now. All right, so modify the code in this listing to find estimates of beta 0 and beta 1. So I guess that means that you have some actual data. All right, I'm just going to guess that. Maybe that's in the book. Directly via the pseudo inverse. Now here you're given this beta with a hat on it. That's defined to be this vector, the pseudo inverse times y. Now I believe that y should be what's on the right-hand side of what I calculated earlier. So I'll just display that again, right? So if I go back and look at what I did with the calculus in the beginning here, so if we take this over to the other side, but notice here that everything has a 2 in it, right? So you want to cancel the 2's, right? So the vector y should be these two sums right here, this one and this one, without the 2's there, because you'll cancel the 2's throughout. Okay, so that should be the vector y that's here. And then this is the usual pseudo inverse that we talked about up here. All right, so you're modifying the code to find estimates of these two using the pseudo inverse. Now I'm guessing that just means you multiply those out and then you have your estimate straight away. So, but in those sums, the sums that we have in the vector y, they involve the x points and the y points, right? So, and of course, so does the pseudo inverse. So yeah, you've got to have that data in order to calculate it. Okay, so but here we see some more information. Beta hat is the vector of length 2, all right, because it has beta 0 and beta 1 in it. And y is the vector vectors containing all the y data. Okay, great. So that's exactly what we expect. So for each of the 4 data sets, find the point with the highest leverage. Okay, and I guess the highest leverage means highest diagonal element of the H vector, which, so that pertains to this one. The maximum diagonal element in this matrix. Okay, so I guess that means that you've just find that piece of code in the book and do the modifications, and it should be relatively easy for you. So let's have a look now at question E. Assume now that you wish to fit this quadratic function, but here you see we've got beta 0, beta 1, and beta 2. Okay, here the design matrix is n by 3. Repeat the fitting of this, okay, so that's this stuff. Using this type of model, display your fit model graphically. So I've got a couple of things to say about that, but I'll find my notes on it here. Fold this so I don't show too much. All right, so what I'm going to show you here is n by 3, right? So that's this matrix right here. So basically, you just append on another column to the other one that you had. So now that last column involves x1 squared, x2 squared, dot, 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 xn squared. And so you're basically expressing the solution beta 0, beta 1, beta 2 in a way like you did for beta 0, beta 1, but then you've got to implement that in Julia, you know, using the modified code that's given in the book. And then Yoni has another comment here. So he says, see the end of the lecture after quiz 2 for plotting with Julia. So there's some specific information on how to get your plots to work in that lecture, right? Because here we see at the end of that question, display your fit model graphically, right? And so if I were to plot this, I would display the data and I would display the actual plot of the quadratic in the same plot, all right? That's what I would want to do there. Okay, so let's have a look at F now. Now F, assume now that you have f of x is equal to beta 1 times x and no intercept term. So in other words, the intercept term is 0. Derive a formula for the optimal beta 1, again using pseudo inverse, this time with the matrix, this one. Okay, so your design matrix here is x1. It's a column vector x1 through xn. So I've just done some calculus here, but this is not actually what you want. Right, so what you actually need to do is calculate this with the pseudo inverse. So in other words, what you're doing is you should calculate A transpose A inverted times A transpose equals, what is it in this case, right? And that should be easy to do because you're just doing that with this column vector. And then, you know, how does that work out with the solution that you get, right? So what does your solution beta look like in that case? Remember, you've only got one thing, just beta 1 alone. So that should be fairly simple. You should end up with one thing divided by another thing. Okay, so I think that's all to say about that. That question F should be fairly easy for you, Jing Yi. Any other questions?
No, thank you.
Are you still there with us, Jing Yi? Maybe your mic's not on, incidentally. So, okay, thank you. So if there's anything else we can do for you now at this point, just let us know. All right, I guess then if you don't have any questions, we'll finish up here because you tell us that you've already done the rest of the questions, and so you only had some problems with question 1. So congratulations on that effort. And so we'll say goodnight to you now. All right, thank you. I see now that you've said in the text, no, you don't have any more questions. So, all right, so thanks so much, and we'll see you next time. I think there's a break next week. Is that right, Walla? Yep, there's a break next week, so we'll see you after a week. All right, good night.